We're ready for Section 6 of Chapter 2. Section 6 is all about solving polynomial equations using factoring in quadratic form. This is just part 1. We're going to do a lot of examples. First method I'm going to show you is factoring by grouping. Now this usually involves 4 terms. Could be more, but usually 4 terms. Sometimes, though, you need to be careful. You have to reorder the terms to make the grouping work. So let's try this first one. Now notice, this is x to the 3rd power. That means we better end up with 3 roots. We better get 3 answers by the time we're done. When you group, you take the 4 terms and you split them right down the middle. You split them right down the middle. And then you look at just the first side. And you ask yourself, what's the GCF of the first side only? Well, they have x squared in common, so pull out x squared. That leaves you with x plus 5. Now, if grouping works, then when you look at the second side and you pull the GCF out, which is negative 4, you'll be left with another x plus 5. If you can make it so that this factor and this factor are the same, then grouping worked. Then what you can do is undistribute the x plus 5 and rewrite this as a product of 2 factors. X squared minus 4 and x plus 5 go together. Well, one of these zeros, or roots, is just negative 5. X squared minus 4 factors to x plus 2 and x minus 2. And so your roots there are negative 2 and positive 2. And sure enough, we got our 3 roots, didn't we? And negative 2, 2, and negative 5. Go ahead and tell me that this is 3 real rational roots. Again, rational numbers are any number that can be written as a fraction. 3 real rationals. Let's do a couple more. So look at this first example. Again, you have the degree is 3, so we have 3 roots we're trying to find. Split it down the middle. In the first half, you can pull out x squared again. Leaves you with 2x minus 1. Now, in the second half, we almost have 2x minus 1 already, except we have negative 2x plus 1. So pull out negative 1, and that leaves you with 2x minus 1. And dun-dun-dun-dun, it worked, didn't it? So when I rewrite this as a product of 2 factors, x squared minus 1 times 2x minus 1. X squared minus 1 factors further. Man, we can just factor this problem. Makes me happy, happy, happy. Alright, so my zeros are x could be plus or minus 1, or it could be positive 1/2. And again, I have 3 real rational roots. They're irrational if you're left with some nasty decimal, like the square root of 7. Let's try the last one. Split it down the middle, like so. In the first half, you can pull out x squared once again. Boy, that's just a coincidence that it continues to be x squared. You will get different GCFs in the first half. In the second half, you can pull out a 4, which leaves you with 2x, minus 3. Hey, it worked again. Dun, 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 dun. Alright, so I have x squared plus 4 as one of my factors. And 2x minus 3 is my other factor. Now x squared plus 4, he doesn't factor. You can't break them up. He's in love. So you're going to have to deal with him a different way. You're going to have to set him to 0. Subtract 4 from both sides. And then take the square root of both sides. So x is actually plus or minus 2i. Right? Do you get that? You take the square root of both sides. And then the other root came from the 2x minus 3. That's 3/2. So those are our 3 roots, which we knew we needed 3. Only one of them, one real rational, that's the 3/2. And the other 2, we have 2 complex roots. And complex roots always come in pairs. So you'll never have an odd number of them. You'll either have 2 of them, or 4 of them, or 6 of them. So we're done with grouping. Let's move on to quadratic form. Now, if you are attempting to use this method, hopefully you have something that factors. You may end up having to use the quadratic formula, though. But I'll ask a couple other tricks that I'm going to show you. Now, this first problem says x to the 4th minus 3x squared minus 4. first, I want to do this problem. I want to do x squared minus 3x minus 4. Now, how does that factor? Well, the same way it did in Algebra 1. 4 and 1 multiply to get 4 and subtract to get 3. And so your zeros would be 4 and negative 1. Well, this works very similarly, only instead of breaking it down to x and x, we're going to use x squared and x squared. We're still going to use 4 and 1. Now, note here that we're looking for 4 roots. We better have 4 answers by the time that we're done. Alright, so our factors are x squared minus 4 and x squared plus 1. Well, set both of those to 0. And solve. Take the square root of both sides, you get plus or minus 2. And this side, you get plus or minus I. So we have our 4 roots. There's 2 of them. There's the other 2. We have 2 real rational roots. I'll abbreviate it with the prefix rat. And we have 2 complex roots. So if you were to graph this function, x to the 4th minus 3x squared minus 4, you would only see it touch the x-axis 2 times. You'd see it touch at positive 2 and negative 2. The other 2 roots are complex. You wouldn't actually see them on the graph. Alright, number 5. Here we go. So we got x to the 4th. It breaks down to x squared and x squared. Now, what multiplies to get 8 but subtracts to get 7? Either 4 and 2 or 8 and 1. 8 and 1. What'd you say, guys? Oh, you said 8 and 1? Oh, well, that's a pretty good guess. 8 and 1. Subtract the 8 and add the 1. Subtract the 8 and add the 1. So x squared will equal 8 when you set it to 0. And x squared will equal negative 1. So x could be plus or minus I again. But the x squared equals 8, you got to take the square root of both sides. The square root of 8 is plus or minus. Remember, 8 breaks down to 4 times 2. So a 2 gets out of jail and a 2 stays in jail. So x could also be plus or minus 2 radical 2. Now describe these roots to me. Well, the i's are obviously complex because they involve complex numbers. The 2 radical 2, though, those are real, but are they rational or irrational? Well, they're irrational. They're nasty decimals that continue on to infinity. So they're 2 real irrational roots. 2 real irrational roots. Dun 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 dun. Alright, nicely done. Okay, let's kick it up a notch with the next one. If you break down 2x to the 4th, you could have 2x and x. And we need to find a combination from 20 such that they subtract to get 3. Well, what multiplies to get 20? 5 and 4, right? 5 and 4. Let's see if that works. 2 outers, 2 times 4 is 8x. And 5 times x is 5x. Oh, you know what? And we can make positive 3x if the 8 is positive and the 5 is negative. So make him negative and him positive. Sweet. So here, oh, by this way, these should be x squareds. Look at me. So x squared is equal to positive 5 over 2, and x squared is equal to negative 4. Well, when you take the square root of the one on the right, you just get plus or minus 2i. So that means we're going to have 2 complex roots there, 2 complex roots. But the one on the left, let's take the square root. So you get x equals plus or minus the square root of 5 halves. Now, that's a big no-no. Do you know why it's a big no-no? Because you have a radical in the denominator. This is the same thing as saying plus or minus the square root of 5 over the square root of 2. And you're not allowed to leave in a radical in the denominator, at least not in this class. Maybe in calculus. So what we're going to do is rationalize. We're going to multiply by the square root of 2 on the bottom and the top. That gives us the square root of 10 on top over the square root of 2 times the square root of 2 is really the square root of 4, which just happens to be 2. That's a little shortcut you can take. Square root of 2 times square root of 2 is just 2. And make sure you throw your plus or minus in front of that. And, by the way, those roots, they're real, but they're irrational. So 2 real irrational roots. 2 real irrational roots. Okay, this is where it gets fun. So, this time we have x to the 6th. Now, if you break down x to the 6th, you get x to the 3rd and x to the 3rd. We need something that multiplies to 27 but subtracts to 26. Well, that's pretty easy. That's 27 and 1. The 27 needs to be positive and the 20 and the 1 needs to be negative. And now you're asking, where in the world do I go with this? Well, there are some formulas that you should have seen back in Algebra 2. One of them is the factoring the sum of 2 cubes formula. The other one's the difference of 2 cubes formula. This is similar to factoring a difference of squares. That's the easy one that we all remember. The differences and the sum of cubes, these are a little bit trickier. So if you have 2 perfect cubes, a cubed and b cubed, those are both perfect cubes, right? They factor to the following. You take the first factor, it'd be a plus b. So it's the cube root of a cubed and the cube root of b cubed, and you keep the plus. Then you're going to need a trinomial. And this comes from square the first guy, so that's just a squared. And then switch your signs, so now he goes minus. And then multiply this guy times this guy, a times b. Well, that's just ab. And then go back to your plus, okay, and then square the second guy, square b. So you have b squared. That's how to factor a sum of 2 cubes. That's the generic formula. To factor a difference of 2 cubes, it's very similar, only the signs are different. Instead of plus minus plus, it's minus plus plus, minus plus plus. Okay, so it would be the square root of the first guy, which is a, minus the square root of the second guy, which is b, and then square the first guy, that's a squared, and it's plus the product of the cube roots, ab, plus the second guy squared. Alright, let's see if we can put these formulas down here into action up here. Well, this first guy is a sum of cubes. He's a sum of cubes. See the plus sign? So here we go. Let's break him down. The cube root of x cubed is x. The cube root of 27 is 3. Put a plus sign. That came from right here. Now, let's try this part. What you do is you square the first guy, so that'd be x squared. Then you subtract the product of both cube roots. X times 3 is just 3x. Then you square the second guy, so you square the 3, that's plus 9. Looky there. That's cute. That's cool. Okay, now let's factor the difference of cubes. He's a difference of cubes, so use this formula down here. Okay, the cube root of x cubed is x, the cube root of 1 is 1, and we leave the minus sign, times the first guy squared is x squared, plus, look down here in the lower right, plus the product of the 2 cube roots, so it's plus the product of x times 1, so it would be plus x, and then plus the second guy squared. Sweet. Alright, now check this out. We know 2 of our zeros. One of them is negative 3, and one of them is positive 1. Put a box around those. Check it out. You got 2 of your roots, but unfortunately there are 6 roots, and we've only found 2 so far. And another unfortunate part is that this dude right here and this dude right here, they don't factor. So you're going to have to use the quadratic formula to solve those. This is a pretty involved problem, isn't it? So here we go. X equals, the opposite of b is 3, plus or minus the square root. B squared is 9, minus 4 times a, which is 1, times c, which is 9, all divided by 2 times a, which is just 2. That gives us 3 plus or minus the square root of 9 minus 36, which is negative 27 inside there, all over 2. That breaks down to 3 plus or minus. When you break down negative 27, you get 3i radical 2. No, that's not right. It'd be 3i radical 3 because 27 is 9 times 3. Sorry about that. It'd be 3i radical 3. And then just put each of those over 2. And if you want to put the I, let me erase that part. If you want to put the I out back, you can. So there's 2 more roots. But remember, how many are there total? Well, there's 6 total. So now we're going to have to use quadratic formula on this guy. X equals the opposite of b plus or minus the square root. B squared is 1 minus 4 times 1 times 1 is just 4. Over 2 times 1 is just 2. So that's negative 1 plus or minus the square root of negative 3 over 2. Well, that's negative 1 plus or minus the square root of 3 with an I after it, both over 2. So those are also roots. Sweet. Now we finally found all the roots of this polynomial. Okay? This guy and this guy, those were real rational. 2 real rational. And the other 4 were all complex because they all involve the imaginary unit, the I. That was an awesome problem. Alright, difference of cubes formula, sum of cubes formula. You saw them in Algebra 2, whether you remember it or not, you did see them. Alright, and the last one, and this one's not quite as bad. A little bit tricky, but not terrible. The thing about this one is it does not factor. It doesn't factor. So what we're going to do is we're going to trick the problem. Instead of it saying x to the 4th, I'm going to use some substitution. Watch this. I'm going to let y equal x squared. I'm going to let y equal x squared. Check me on that. That means instead of just plain old x squared, I'm going to have plus y in the middle, minus 1. And instead of x to the 4th, I'm going to have, I would have x squared squared, which is just like having y squared. Think about that. If y equals x squared, then y squared is x to the 4th. Y squared. Or you can think of it like this. Y squared is the same thing as x squared squared, which again is just x to the 4th. Well, now this, although it doesn't factor, we can use the quadratic formula. But instead of x equals, it's y equals now. So opposite of b is negative 1 plus or minus the square root of b squared is 1 minus 4 times 1 times negative 1, all divided by 2 times 1. Well, that's negative 1 plus or minus the square root of 5 over 2. And what you're going to have to do on this one is go ahead and approximate these answers. Y could be about 0.618. Do this on your calculator. Or it could be about negative 1.618. We got a problem. The problem is, guys, this was a quartic polynomial. Look on the top of the screen. It was a quartic. And we only have 2 answers so far. But wait a minute. These are what y are. I'm more interested in what x is. So I'm going to set set these equal. Well, let me not say set. I'm going to substitute back in for y. Check this out. So 0.618 is really x squared. And negative 1.618 is also x squared. But I don't want x. I want you to take the square root. Type that in your calculator. You're going to get plus or minus, careful, about 0.786. 0.786. And here, careful here, take the square root of this negative, but factor out the negative, make it an I. You're going to get x as plus or minus. Remember, the negative comes out, becomes an I. About 1.272 when you type that into your calculator. You had to put that in your calculator. And here we have 2 real irrationals and 2 complex. 2 real irrationals and 2 complex. Okay, so our methods that we discussed were factoring by grouping and factoring using something called quadratic form, where you take quartic equations or sixth degree equations and you force them to look like quadratics. You kind of cheat. You kind of outsmart the problem. Makes you feel kind of good, doesn't it? Next video, I'll show you the third method, and it's probably my favorite one because it always works. Anyway, hope you had a good time. I enjoyed it. Hope you did too. Get some rest. I'll talk to you later. I'm out.